In this video, we're going to expand our look at probability distributions, shifting to the normal curve. Now, we previously saw that we could create a probability distribution based on the probability of obtaining different numbers of heads flipping coins. This was specifically a binomial probability distribution with 0.5 probability of success, because our outcome only had two possible outcomes, heads or tails, and the probability of obtaining a head was equal to 0.5. At the time, we noted how it started to look more and more like a normal curve as the number of flips increased, or the number of trials increased if we use the language of the binomial distribution. And notice it's a little lumpy and it kind of appears in steps because the number of flips it's not a continuous variable. You have 1, 2, 3, or 4, etc. flips. You can't flip a coin 3.932 times, right? But again, as the number of flips increased, as our number of trials increased, the binomial probability distribution becomes closer and closer to a normal curve. But that's not where the similarities end. In fact, the normal curve is also a probability distribution. And if you think about it, it may not be that surprising at this point. I mean, we've already used the normal curve to estimate the proportion of people above or below a given score. If instead we think of it as a sampling experiment, and remember that term from earlier videos, if I randomly sample someone, instead of proportions above or below some score, I can interpret the same values as the probability of sampling someone above or below a given score. The ability to use the normal distribution as a probability distribution opens up a lot of opportunities for statistical analyses. For now, let's start by seeing how easy it is to estimate probabilities based on the normal distribution once you're familiar with the normal curve and z-scores. Let's illustrate this with a fairly straightforward and common type of question based on the well-understood properties of SAT scores. We'll assume that the mean SAT score is 1060, 1060, with a standard deviation of 190. What's the probability that someone has a score above 1200? We begin by calculating the z-score for an SAT of 1200. And we know the z-score formula is z equals our observed x minus the mean of x divided by the standard deviation. In this case, it's z equals 1200 minus 1060 divided by 190, or 140 divided by 190, which gives us z equals 0.737. So the z-score for an SAT of 1200 is 0.737. We can visualize this question using the normal curve, right? We just find a z of 0.737 on the normal curve. We're interested in the area above a z of 0.737, this shaded in blue area, right? And using either Excel or a normal distribution table or something, we can find that the area above a z of 0.737 is equal to 0.231. That tells us, right, that 23.1% of the people have a z-score greater than 0.737. Now, if we shift gears a bit and think about this again as a sampling experiment, if I randomly sample someone from this distribution, and we know 23.1% of the distribution is above a z-score of 0.737, then the probability of randomly selecting someone above a z-score of 0.737 is 0.231, right? Or translating it back to our original language of SAT scores, we can say that the probability of someone scoring above an SAT of 1200 is equal to 0.231. Remember, the z of 0.737 is the same thing as an SAT of 1200. They're just different statistical languages. It's like escargot in French is the same as snails in English. Well, okay, not the same thing, but you get what I mean, right? Okay, pretty straightforward, right? We're doing the same thing that we did before, but now talking about the probability of someone being above a certain point rather than the proportion of people who are above a certain point, right? Let's do one more example using SAT scores. And we'll stick with a mean SAT of 1060 with a standard deviation of 190, but instead, let's ask for the probability that someone will have a score below 800. Right? We begin by calculating our z-score for an SAT of 800. In this case, it's z equals 800 minus 1060 divided by 190, or negative 260 divided by 190, which gives us a z of negative 1.368. So the z-score for an SAT of 800 is negative 1.368. And again, we can look at this visually, right? All we need to do is find the z of negative 1.368 on the normal curve. We're interested in the area below a z of negative 1.368, right, which is this shaded in blue area here. Then we just use Excel or a calculator or a normal distribution table to find that area below a z-score of negative 1.368, that area is equal to 0.086, right? If I'm randomly selecting someone from this distribution, and everyone has the same chance of being sampled. Remember, 8.6% of the people are below a z-score of negative 1.368. So the probability of randomly selecting someone below that z-score of negative 1.368 is 0.086, right? You can translate that z-score back to SATs as the probability that someone has a SAT below 800 is equal to 0.086. And again, remember, a z of negative 1.368 is the same thing as an SAT of 800. It's just escargot and snails again, right? Now, before wrapping up, let's step back for a moment and take a big picture look at the whole area idea, all right? Remember, this is all based on the area under the normal curve. If you used calculus and calculated the area under the normal curve, all of it, from negative infinity to positive infinity, all of that area would add up to 1, or a probability of 1. There's a 100% probability that any result is somewhere under the curve. And by any result, I mean any result. In this example, our result is someone's SAT score, but it could be anything we're studying, behavior problems, reading skills, aerobic capacity, any result of anything we're studying, right? Now, because the area reflects all of the probabilities, the area in different parts of the curve tell you the probability of getting a result in that range. In this example, someone having a SAT score above or below some given level. If it's a small area, maybe a little bit out in the tails like we see here, it means it's a small probability of getting a result in that range. On the other hand, if it's a large area, maybe something overlapping a large part of the middle, it means there's a large probability of sampling someone or getting a result in that range. So you see, it's very similar to what we have previously been doing with z-scores in terms of the proportion of people above or below a given z-score. Now we're just using the same normal curve to estimate the probability of sampling someone or something or getting some result that's above or below a given z-score. And of course, the same language and magic words that we've previously discussed apply here as well, whether it's the probability above a given score or below a given score or more extreme than a given score, two tails, or bounded by the plus and minus sign values of a given score. It still all applies here. All right? We're just talking a little more abstractly about probabilities of sampling in some range of z-scores rather than the proportion of people in that range. It may seem like a small little twist, and to be honest, if it does, that's a good thing. But as we'll see shortly, it's a powerful twist that will let us estimate the probability of things happening, like the probability that a new literacy intervention actually helped kids read better. That's where stats really starts to get exciting. And with this material now behind us, we've started that journey now.
That's good. You've taken your first step into a larger world.